Hi, I'm Hyunkook from University of Huddersfield. What I'm going to talk about in this presentation is the effect of direct-to-reverberant energy ratio on front-back confusion in binaural reproduction. So just to give a brief background, this is a common problem in binaural reproduction that front and back sources get confused when we try to localize them. So sources in front of the listener can be sometimes perceived as if it was in the back of the listener, vice versa. So back source is located in front instead of the back. So this kind of reversal error is a common issue that is discussed a lot these days. In real world, we localize sound sources not just by auditory cues, but also by using head movement and also visual cues. But in synthetic environment, in binaural listening, head tracking and individualized HLTF can be useful for avoiding such a reversal error. But non-head tracked binaural audio with generalized HLTF is still being used widely, so it's important to consider this kind of non-head tracked scenario where front and back confusion can be more serious. Previous research on front and back confusion mainly focused on spectral cues, but more recently there was discussion about the effect of reverberation on front and back confusion. So front and back confusion might be less problematic or more problematic depending on the conditions in a reverberant room compared to in an anechoic chamber. And as widely known, the direct reverberant ratio, in short we will call DRR, is an absolute cue for auditory distance perception. And previous research found that source listener distance in a room has a certain effect on front and back confusion rate. So the first question we asked in this present study is, what is the effect of DRR, direct reverberant ratio, on front and back confusion in binaural reproduction? And what are the potential thresholds of DRRs in terms of front and back confusion and back to front confusion? And is there an optimal range of DRR to avoid strong front and back confusion, which we can exploit in practical binaural recording and mixing? So to answer these questions, we designed an experiment. The main motivation was virtual loudspeaker monitoring in 3D audio production. So on headphones, you can listen to loudspeakers virtually and monitor your mix or your music production over headphones. So binaural room impulse responses for 0 degree and 180 degrees. So directly in front of the listener and the back of the listener, captured in an ITUR BS 1116 compliant room. You see this photo here. The reverb time was 0.25 seconds. We used KU100 dummy head microphone placed in the middle of the room, 2 meters from each speaker. And the original BRIRs were segmentized and manipulated in terms of DRR. So we used the cutoff boundary point of 2.5 milliseconds as used in other previous research, for example, by Zahoric. So 2.4 millisecond basically avoids the first reflection in the direct sound part, and the rest of the signals was segmented as reverberation. And DRRs ranged from minus 12 dB to 12 dB with 4 dB intervals by adjusting the level of the reverberation part. And in addition, we also created pseudo-anechoic condition, basically had no reverberation. And the manipulated BRIRs were convolved with a train of pink noise bursts, and all of the stimuli were RMS normalized. 5 subjects participated in the listening test. All of them self-reported normal hearing, and they were all experienced researchers in spatial audio, ages ranging from 24 to 43. We used a forced choice method using this listening test generation tool called Hultgen version 2. The task was to choose either front or back for each trial for a given stimulus. In each trial, the listener was forced to choose either front or back. And each listener tested each stimulus 20 times in total in a random order. Everyone used K702 headphones with equalization applied. The test was conducted remotely at the subject's home due to the COVID-19 pandemic. They were all in a quiet room, and when they listened to the stimulus, they were advised to close their eyes strictly while listening. We devised a novel playback level calibration procedure for remote testing as follows. Firstly, I recorded hand rubbing sound like this and convolved it with HRIRs of 0 degree azimuth and elevation. And I set my audio interface level to calibrate this stimuli to 68 dB LAQ using an ear simulator. And at that level, the RMS level of the hand rubbing recording was loudness matched to actual hand rubbing myself. And each subject first adjusted their audio interface output level so that the provided hand rubbing matches their own hand rubbing in terms of perceived loudness. And this procedure was expected to make the playback level roughly around 68 dB LAQ. Assumption is that everyone's SPL of hand rubbing sound might be quite similar. And this is the result from the listening test for each subject. So as you can see, they exhibit very consistent patterns across all 5 subjects. So the upper panel shows the results for the front source. So source at 0 degree azimuth. The percent correct from 0 to 1. As you can see, as the DRL increases, the PC also tends to increase. But for the source in the back, the PC tends to decrease as the DRR increases. So front and back sources demonstrate the opposite patterns. And the dashed line basically indicates the 0.5 threshold point. Now, combining all of these results just to see a global pattern, now we can see some very interesting trend emerging here. So as the DRR increases, which means there's less reverb, the subject response is tended to be biased to front, regardless of whether the source was in front or at the back. Likewise, as the DRL decreases, which means more reverb, the subject's response is tended to be biased to the back, regardless of the target source position. So they show the opposite pattern. So we can see this trade-off relationship here. At a higher DRR, so basically if we basically shade this region above the threshold of the front source, so around 2 dB above, localization accuracy for source in front would be higher, but that has a trade-off with this front and back discrimination for the back source. So more dry sound basically causes more errors for the back source. That is back to front confusion. But at a lower DRL, we can see that localization accuracy for a source behind the listener would be higher, but that for a source in front would be lower. So we are seeing more of this front to back confusion. So now there tends to be this overlapping area where front and back confusion is neither super high or super low, but it's kind of middle ground here. Now, using this trade-off relationship, we propose this simple model of DRL in terms of front and back confusion. So the XF is the threshold for the front source, which is here, around 2 dB from this current data. And XB is the threshold for the back source, which is around 6 to 7 dB. So we can see that if the DRL is lower than XF, basically this will cause higher chance of front and back confusion for the front source, but it will give higher discrimination accuracy for the back source. So this is the case where there is a lot of reverb. But for a higher DR, which has less reverb, we can expect higher discrimination accuracy for the front source, but higher chance of back to front confusion for the back source. And this middle region is basically about medium discrimination accuracy, or also medium chance of confusion. So what does this mean in practice? So let's consider binaural recording or mixing scenario using binaural room impulse responses. First of all, BRILs would be more useful than HRIL, anechoic impulse responses, in terms of resolving front and back confusion. But how should we use the result? So in this kind of scenario, we can expect a very good front and back discrimination if the front source is close enough to the listener. In other words, DRR is above the XF. And for the back source, it needs to be far enough from the listener in order to avoid back to front confusion. So in this kind of scenario, we can have pretty good front and back discrimination, hopefully. But in this opposite scenario, where front source is too far from the listener and back source is too close to the listener, now this case will probably create strong front and back reversals for both sources. So the accuracy and confusion will be stronger in front and back localization. And this study is still ongoing. A larger number of subjects will be employed to obtain a more reliable global psychometric function of DRR on front and back discrimination. And we're also going to measure people's hand rubbing SPLs to see how much they vary person to person, and we'll attempt to validate the proposed remote playback level calibration method using hand rubbing recording. And thank you very much for listening. If you have any questions or any discussions, please email me and visit our website, follow us on Facebook, and subscribe to our YouTube channel as well. Thank you very much.